Hello everyone, in the first two classes, we learned the concept and general formula of arithmetic sequences. In this lesson, we will use this knowledge to solve the problem of summing arithmetic sequences. Let's start with a story about the famous German mathematician Gauss when he was a child. It is said that more than 200 years ago, Gauss's arithmetic teacher asked students to calculate what 1 plus 2 plus 3 equals until it reaches 100. While other classmates were still busy adding up these 100 numbers one by one, 10-year-old Gauss quickly calculated the correct answer. Do you know what clever method Gauss used? Because Gauss found that the sum of the first term 1 and the last term 100, as well as the sum of the second term 2 and the second to last term 99, are all 101. The same applies to the third item and the third to last item, until the middle two items, namely the 50th item and the 50th to last item. So he changed the order of the calculations and pieced together the numbers with a sum of 101 to form a pair. He then added them up in pairs, resulting in 50 101 seconds added together. Thus, the result of 5050 was quickly calculated by multiplying 101 by 50. So why does 1 plus 100 equal 2 plus 99 and always equal 50 plus 51? Is this a coincidence? Can you try to provide an explanation from the perspective of a sequence? In fact, if we set a n equal to n, then 1, 2, 3 all the way up to 100, that is, a 1, a 2, a 3 all the way up to a 100. The problem posed by Gauss's arithmetic teacher is to find the sum of the first 100 terms of the sequence n. Gauss's algorithm utilizes the principle that a 1 plus a 100 equals a 2 plus a 99, and always equals a 50 plus a 51. If you remember a conclusion we proved in the last class, you know it's not a coincidence. The sequence a n is an arithmetic sequence, so the subscript and the sum of two equal terms are equal. Gauss cleverly utilized this property to transform the problem of summing different numbers into a problem of summing the same number, thereby simplifying the operation. Can you use Gaussian method to calculate 1 plus 2 plus 3 until it reaches 101? We still pair the first and last terms together, and the second and penultimate terms together, and we find that both are 102. How many pairs can those 101 items make up? Due to the odd number of items 101, only 50 pairs can be formed, and there will be one item left to be calculated separately. The 50th pair should be 50 plus 52, the remaining item is 51. Therefore, adding 50 pieces of 102 together plus 51 equals 5151. Can you think of any other methods? We can sum the first 100 terms by pairing them together, resulting in 5050, and add the last term 101, which equals 5151. We can also add a term of 0 at the beginning and convert it into a sum problem of arithmetic sequences with even number of terms. Then, we can use Gaussian head-to-tail pairing to pair 0 and 101, and 1 and 100. So we can match these 102 items into 51 pairs. The sum of each pair is 101. So it's equal to 101 multiplied by 51 equals 5151. Perhaps everyone will come up with other methods, most of which are equivalent to utilizing the property of arithmetic sequences, subscripts, and equal terms. Converting the sum of different numbers into the sum of the same number, using multiplication instead of addition, improves the efficiency of the operation. Next, we will extend this method to general situations and try to calculate 1 plus 2 plus 3 until it reaches n. Based on previous experience, the solution to the problem is slightly different when the number of items is odd and even, so we will classify and discuss the parity of the number of items here. When n is even, we can pair the beginning and end to form half-n pairs. The first pair is 1 and n. The second pair is 2 and n minus 1, and the last n pair is half-n and half-n plus 1. The sum of each pair is 1 plus n. There are a total of half-n of 1 plus n, so the result is n multiplied n plus 1 divided by 2. When n is odd, we can choose one of the previous methods. For example, we first calculate the sum of the first n minus 1 term, and then add the nth term. That is, subtract 1 from Sn and add n. Since n is odd, subtracting 1 from n is even. We can use the conclusion we just discussed when n is even. By replacing n with n minus 1, we can obtain Sn minus 1, which should be equal to n minus 1 multiplied by 1 plus n minus 1 divided by 2, that is n. Simplification yields half n multiplied n plus 1. Observant students may have noticed that when n is odd, our conclusions are consistent with those when n is even. So for any positive integer n, we have 1 plus 2 plus 3 added up until n equals n multiplied n plus 1 divided by 2. Why do we classify and discuss the parity of the number n, and the resulting expression is consistent? Is there any inherent pattern in this? Can we reach a final conclusion through unclassified discussions? If we multiply both sides of the formula in the conclusion by 2 at the same time, we can obtain a sum of 1 to n, which is equal to n times n plus 1. This means that adding to Sn equals adding n1 plus n. How to combine the sum of two groups from 1 to n into n sums of 1 and n? We compare each item in the first Sn with each item in the second Sn, using 1 to match n, 2 to match n-1, 3 to match n-2, and so on until n matches 1. To better represent this correspondence, we will reverse the order of the summation terms in the second Sn. So, we get 2Sn added together, which means we can add the two corresponding terms above and below, and the sum of each group is 1 plus n. Therefore, it is equal to the sum of n1 second plus n. It is equal to n multiplied by 1 plus n. In this way, Sn is equal to 1 plus 2 plus 3. Continuously adding n equals n multiplied 1 plus n divided by 2. Can you explain how this method cleverly avoids classification discussions? This method adds 2Sn, one from 1 to n and the other from n to 1 in reverse. In this way, the sum of the corresponding terms is 1 plus n, so that regardless of whether n is odd or even, we can convert the sum of different numbers into the sum of n identical numbers. This method is called the reverse order sum method. We can also experience this method geometrically. We need to calculate the total number of steel pipes in this pile. Given that there is one steel pipe in the first layer and two in the second layer, starting from the second layer, each layer has one more steel pipe than the previous layer, until there are n steel pipes in the nth layer. So the total number of steel pipes in this pile is Sn, which is equal to 1 plus 2 plus 3, all the way up to n. We can imagine that if we invert another pile of identical steel pipes and splice them together with the original pile, the number of steel pipes on each layer will be the same, 1 plus n. There are a total of n layers, so the total number of these two piles of steel pipes, which is twice the Sn, is equal to n multiplied by 1 plus n. Therefore, the total number of steel pipes in a pile, Sn, is equal to n multiplied by n plus 1 divided by 2. The method of reverse summation is very clever. Can it be used to find the sum of the first n terms of a general arithmetic sequence n? Let's give it a try. Let's first represent Sn as adding from item 1 to item n. Represent Sn as adding the nth item to the first item. The sum of the two equations gives twice the value of Sn, which is equal to the sum of a 1 and a n plus the sum of a 2 and a n minus 1, and continues to add to the sum of a n and a 1. Due to the fact that the subscripts of arithmetic sequences are equal to the sum of two terms that are equal. Therefore, twice Sn is equal to the sum of n a 1 and a n, which is equal to the sum of n times a 1 and a n. So Sn is equal to half n times a 1 plus a n. This is the antecedent and formula of the arithmetic sequence n. Can you describe this formula in written language? We can express it as the sum of the first n terms of an arithmetic sequence is equal to the sum of the first and last terms multiplied by the number of terms, and then divided by 2. This indicates, as long as we know the first, last, and number of terms, we can calculate Sn by taking the first n terms of the arithmetic sequence and formula 1. For example, in the arithmetic sequence n, given that a 1 is equal to 7 and a 50 is equal to 101. Find S50. We know the first and last items here, and the number of terms n is actually implicit in the index, where n equals 50. Substituting them into formula 1 for calculation, S50 is equal to 2700. In fact, in Formula 1, there are 4 quantities: the sum of first n terms, the first term a1, the last term a n, and the number of terms n. From the perspective of the equation, we know that any 3 quantities can be used to obtain the 4th quantity. Next, let's slightly modify the formula to see if we can make any new discoveries. We divide both sides of the equation by the number of terms n at the same time, and the result is that Sn divided by n equals 2 parts a1 plus a n. What does this formula mean? On the left side of the equal sign, we can also write it as the sum of a 1 to a n divided by n. Its meaning is the average of the first n terms, and the sum of a 1 and a n divided by 2 on the right side of the equal sign is the average of the first and nth terms. The meaning of this equation is that the average of the first n terms of an arithmetic sequence is equal to the average of the first and n terms. We know that if the first term and tolerance of an arithmetic sequence are known, then this arithmetic sequence is completely determined. The sum of the first n terms is naturally determined. Can we use the first term and tolerance to represent the first n terms and? It is not difficult for everyone to think that we only need to represent n in Formula 1 as the first term and tolerance. The general formula n for arithmetic sequences is equal to a 1 plus n minus 1 times d. Substitute it into Formula 1 to obtain such an equation. We will remove the parentheses from the molecule, organize and obtain n times a 1 plus n multiplied by n minus 1 divided by 2 times the tolerance d. This way, we obtain the first n terms and formula of the arithmetic sequence represented by the first term a 1 and the tolerance d. We denote it as Formula 2. If you don't use the conclusion of Formula 1, do you have any other ways to obtain Formula 2? We can go back to the definition of Sn and simply represent each term of the sequence with its first term and tolerance. According to the general formula of arithmetic sequences, a 2 is equal to a 1 plus d, a 3 is equal to a 1 plus 2d, and a n is equal to a 1 plus n minus 1 times d. We found that there is one a1 in each item, a total of n a1, and there are still 1 plus 2 added to n minus 1 and so many times the tolerance d. Substituting it in, Sn is equal to n times a 1 plus n multiplied by n minus 1 divided by 2 times d. We also obtain Formula 2. Through this process, it should be easier for everyone to understand the meaning of the coefficients a1 and d in the formula. According to Formula 2, we can calculate the sum of the first n terms of the arithmetic sequence by the first term and the tolerance. Similar to Formula 1, Formula 2 also involves four quantities: the preceding clause and Sn, the number of items n, the first item a1, and the tolerance b. Given any three of them, we can calculate the fourth one. For example, in the arithmetic sequence n, given that a1 is equal to 1/2, b is equal to -1/6, and Sn is equal to -5, find n. We note that all four quantities involved in this problem appear in Formula 2. So let's substitute them into Formula 2. You can get an equation about n which is organized as n squared minus 7n minus 60 equals 0. Solve that n equals 12 or n equals -5. Here it should be noted that in sequence problems, the number of terms n is a positive integer, so n can only take 12. So far, we have obtained two formulas for the sum of the first n terms of the arithmetic sequence. You may have noticed that these two formulas involve five quantities: the first n terms and Sn, the number of terms n, the first term a1, the last term a n, and the tolerance d. Two equations can solve for two unknowns, so knowing any three of these five quantities can solve for the remaining two. Some people may propose a general formula for arithmetic sequences, which is also about the equal relationship between these quantities. Can three formulas solve for three unknowns? In fact, Formula 2 can be derived from Formula 1. Substitute the general formula and organize it. So these three equations are not independent of each other. Any two of them are independent of each other, and we can choose them reasonably according to specific conditions. Now let's take a look at a set of example questions. The known sequence n is an arithmetic sequence. If S10 equals 310 and S20 equals 1220, find Sn. This question involves three aspects, and how should we express them separately? Taking S10 as an example, if represented by Formula 1, it will be transformed into the relationship between a 1 and the final term a 10. If represented by Formula 2, it will be transformed into the relationship between the first term a 1 and the tolerance d. S20 is similar to Sn. We need to establish a connection between the three of them, and obviously we need to represent them all with the first term and tolerance, which determines our problem-solving approach. According to Formula 2, for the sum of the first n terms of the arithmetic sequence, we represent S10 and S20 as the first term and tolerance, and obtain a system of binary linear equations about a1 and d. Solving this system of equations yields a 1 equal to 4 and d equal to 6. Bring a 1 and d back. In Formula 2, for the sum of the first n terms, we can obtain that Sn is equal to 4n plus n multiplied by n minus 1 divided by 2 multiplied by 6. Organize to obtain 3n squared plus n. We found the connection between the condition and the problem through the first item and the tolerance in this question. In fact, the first term A1 and the tolerance B are the fundamental quantities that determine an arithmetic sequence. Any condition of an arithmetic sequence can be transformed into the relationship between the first term 1 and the tolerance d. At the same time, as long as the first term and tolerance are obtained, any problem of the arithmetic sequence can be represented by them, thus obtaining a solution. Therefore, the first term and tolerance are the key to solving the problem of arithmetic sequences. To obtain these two quantities, two independent equations are required. And these two equations need to be given through two independent conditions. It can be seen that as long as two independent conditions are given, the arithmetic sequence is completely determined. This method of solving arithmetic sequence problems by transforming the first term and tolerance into two fundamental quantities has generality. We call it the fundamental method of measurement. In this lesson, we started from the Gaussian method and went through the process of classification discussion. Finally, the method of reverse summation was discovered, and the first n terms of the arithmetic sequence and formula 1 were derived. Then, using the general term formula of arithmetic sequences, we obtained formula 2 by using two methods to represent the first n terms of arithmetic sequences with the first term and tolerance. Any condition and problem of an arithmetic sequence can be transformed into the relationship between the first term and the tolerance, and thus solved. This is the fundamental method of measurement, which embodies the ideas of transformation and transformation. These three formulas involve 5 important correlation quantities in arithmetic sequences. By using two independent formulas, we can determine any 3 quantities and solve for the remaining 2 quantities. This reflects the idea of equations. That's all for this class. Goodbye, everyone.